Thank you, Roy. I'm a applied machine learning researcher at PayPal. We work on variety of problems, applying variety of machine learning techniques like deep learning and graph modeling to solve variety of domain problems. Today, I'm going to be talking primarily about fraud prevention. So the title is Graph-Based Representation Learning. I don't know if people have done the earlier presentation. It was about word embedding. This is about embedding on graph structure, which is primarily node embeddings. So this agenda, essentially, I'll describe the problem of collusion fraud and the approach we take to solve collusion fraud. Conducted some large-scale experiments. I'll share some early findings from those results and conclude my talk. Briefly, what we do for fraud prevention at PayPal, we've been building machine learning models for over 10 years. Our fraud models are state of the art. We constantly evaluate performance of our models with several vendors and outside data sources. They can't come even 10 points close to that, primarily because we have a robust feature engineering engineered over 10 plus years. We have sophisticated machine learning and statistical models. Earlier, we used to have simple linear models to single layer neural network to now we have ensemble of gradient boosted trees and deep learning techniques to build our machine learning models. We have obviously, we process billions of transactions, so we have a highly scalable infrastructure to do fraud prevention and detect and take decisions in real time within a few hundred milliseconds. We have also have a superior team of data scientists. We have data scientists distributed across 3 different locations, Israel, San Jose, and Shanghai. We also have a financial and intelligent analysts who are intelligent analysts come up with the feature engineering aspect of it, and financial analysts make sure the models we built they invoke strategy rules on top of existing models to make sure that they decide different cutoffs for different segments. For example, an area where we are just expanding, we want to have we're okay with observing some loss, whereas in a well-established segments like US, we want to have a more stricter controls around loss prevention. So collusion fraud, I'll give you a simple example. So hopefully everyone is, we're all good here, good people here, right? So don't get any ideas from this example. So simple example is that let's say the buyer purchases an item using PayPal. Seller ships the item to the buyer. Buyer finds the box empty and asks PayPal for a refund. PayPal can refund the buyer because in most cases, we provide buyer protections. No questions asked. We refund the buyer whatever the money they asked for. PayPal asks seller for the proof of purchase. So we refund the buyer, but we want to make sure that we can recover from the seller. So we ask seller for proof of purchase. Seller gives proof like shipping label or so. So we pay, obviously, if the seller has a proper receipt for sending the shipments, because we have seller protection with the most sellers, we also pay the seller. The end result is PayPal incurs loss. And obviously, in this case, buyer and seller can split the money, right? So this we call it an empty box problem. So they send the shipment, but the box was empty. Nothing was in it. Both benefited, but PayPal is the one who is suffering the loss. So this is a simple case of collusion fraud where the buyer and seller are colluding to steal money from PayPal. So we have several examples of collusion fraud. Obviously, what if there are many such buyers? And so we have sophisticated models for transaction level fraud systems. We are constantly, as we build our models, robust models for transaction level fraud, fraudsters move towards a more facilitating network effect to commit more sophisticated frauds. So how can you prevent such a buyers and sellers colluding with each other to steal money from PayPal? What if they do constantly stay below the threshold, for example, making a purchase less than a few $100s or so where it's harder for PayPal to invest time in arguing and with both the seller and the buyer to recollect the money. Instead, so what buyers do is conduct transactions below some transaction threshold. They also move, establish fake credentials, move from one account to the other, one IP address to the other IP address to evade from our fraud prevention strategies. So obviously, if you map this entire buyer-seller IP address, it is a network problem. So this is actually few of the assets which I have put here, but you can imagine that the email address and the domain where they're shipping from, the seller's IP, and so on, many other entities can be represented as node elements, and you can model this as a network problem and solve much more efficiently with network-based analysis and techniques. So that's a goal of this research is to how can we apply some of those sophisticated graph-based modeling techniques to prevent such collusion fraud. So just to give you a brief overview of traditional way you build a machine learning model, you have some raw data, you do expert-driven way to engineer features. And from the features is basically a tabular data. So in a typical supervised machine learning problem, you have a bunch of features and you have a tag. In the fraud prevention cases, you say it's fraud or not fraud as a tag. And you have a whole bunch of features to detect that discriminate fraud versus not fraud. And we apply machine learning algorithms to build a machine learning model. What is deep learning is really powering this space is that the traditional way of feature engineering is gone. Instead of having to engineer features from a raw data set, we can directly take raw data and learn features from the raw data using a deep network architecture. It's called the representation learning or the feature learning, and build models based on those. So this completely eliminated the human intervention of feature engineering aspect, which is what led to the success of deep learning. And this success has been well established in the image processing and the natural language processing domain. But what we work on is large quantities of structured data. That's where what we are exploring is that how can we adapt some of the deep network architecture for our structured data space. So how we do that actually in this, so we have raw data. So for us, raw data meaning that you have PayPal transactions. So every time you log in, sign up, log out, make a payment transaction, each one of those events are the raw data, right? So based on those raw data, we want to, obviously, currently we have expert-driven feature engineering. So what we are, as part of the research, is we are adding additional features learned from a graph network structure. So the representation learning is applied to a graph structure. So it's a structured data format rather than unstructured data like images. And use a combined feature space to build our machine learning model. So still today, even now, for machine learning models, you need to have a features vector, which is in tabular data. So the learned features are fed into our downstream machine learning pipeline to build our supervised machine learning models. For building the machine learning models and stuff, we use we've been heavy users of H2O, which is actually an open source machine learning, large-scale machine learning toolkit. In this, we used driverless AI, which is actually the commercial version of. Behind the scene is all doing is XGBoost to power the machine learning models, but they also have a logic for automatic feature engineering from raw transaction data. So we use that to build the models. That's our high-level approach. So specifically about let me dive deeper into the graph-based representation learning. The goal is actually to, so because our machine learning models, you need to have a features vector. The graph-based representation learning, so you have a graph structure. So be it the goal of representation learning is how can we encode this graph structure into a tabular feature vector. The feature vector is called the embedding. In the natural language processing case, you have word embedding. Here we have a node embedding. What we want to do is we want to generate a continuous feature representation from graph structure data. What we want is, as part of this goal, is that we want to generate a continuous feature representation which is task independent. So we want to learn this representation in an unsupervised way so that be it a fraud or you want to actually apply to other domains, like for example, you want to give credit to a particular person. So how can you use this feature representation for a variety of domain problems? We want to do a domain agnostic way to learn this continuous feature representation. So but what we want is a similarity in the original network space, the graph structure. You want the same similarity should be approximated in the new condensed continuous feature representation space. So there are a variety of methods. There is really one of the state-of-the-art techniques with a lot of improvements happening in the deep learning on the unstructured data space. How can we actually bring deep network to the structured data space like a graph? There are several ways to do it. One is matrix factorization and random walk, and the more emerging one is graph neural networks, specifically graph convolutions, kind of applying convolution functions for graph structured data. So in this, we have been working mainly on the random walk and the graph neural network-based approach. So I don't have conclusive results yet on the graph convolution neural networks. I'm going to share the random walk-based approach. So the graph-based, so there are specific, the high-level methodology is the random walk. The specific technique is a technique developed by Stanford researchers Grover and Leskovich called node-to-vec. So just like word-to-vec, learning a vector representation for words, this is actually learning a vector representation for node elements in a graph. So the key contribution of this research work is that essentially to learn a representation for the nodes, it not only knows, so for example, U is a node, so you want to learn a representation for node U in this case, where the representation for nodes along these neighbors, which is S1, S2, and S3, S4, you want to, all of them have to have a similar node embeddings. It's because they are all in the same neighborhood, right? But node U and node S6 also has a different meaning in this particular network structure. For example, they both follow, have a same role in this network structure. For example, they form something called like a hub. So like an airport hub. So United Airlines, I think Chicago is the airport for United Airlines and Frankfurt is the airport for Lufthansa. So when you generate a node embedding for different airport nodes, you want to have similar embeddings for Frankfurt and Chicago airports. So the same philosophy applies, is that network embedding, you need to have so you want to have a similar representation even though they are not directly connected to each other, even though they are far away from that, if the role they are playing in the network is similar in nature. So that is a key idea behind it. The algorithm basically uses a random walk. So because you can't actually explore every one of those node combinations, you take short random walks. So if you think of a word-to-vec, the way the embedding is, I don't know if you attended the previous talk, is that in order to generate a word embedding for a particular word, you can look at the adjacent words. So let's say that you want to predict what comes after a word home. It'll be home alone, homecoming, home away, and so on, right? You can take a large quantities of corpus of text data, then use the text data to what is the probability at which, what is the target word given you have a home word, what should be the next word. You can predict that using by training a deep neural network on that large corpus of text data. Similar philosophy applies, but only difference between word embedding and the node embedding is in the word embedding. So what you can do is you can use some kind of sliding window. You look at few words before and after to predict the next adjacent words. But the network structure, what you do is you use a random walk. So in particular researchers use a combination of breadth first and depth first search. So if you do a breadth first search, you do this. You can do a community detection within this local neighborhood. So you have a local microscopic view of this particular subgraph. And if you do a depth first search, let's say you walk from U to S4 to S3 to S6, so you have a global macroscopic view. Obviously, it's an approximation technique. Researchers, authors have proven a significant predictive lift in some of the problems they explored. So we thought there'll be a good thing to try for collusion fraud. So our specific implementation framework is that because, as I said, that we take directly from raw events, which is actually a PayPal transaction event, login, logout, and payment transaction events. So one of the challenges of implementing all these frameworks, which were academic research for industry, is that how do we scale for the large quantity of data which we have? So we have all our data in HDFS. So one of the challenges we had was that if you want to learn a representation from graph you need to have the data in consumable form. So because the data is there in HDFS, HDFS is not conducive to applying large-scale graph computing algorithms. So we populated all those events periodically, take those events into a GraphDB. Ideal solution is actually if you have a GraphDB right at the gate whenever an event happens, so we can stick those events into a GraphDB. But right now, we don't have an infrastructure to do that. So we did an offline way to take those events from our HDFS and populate the GraphDB. For GraphDB, we specifically use Neo4j. We evaluated various databases, and Neo4j is built in a scale-up model where we have an infrastructure where we could fit the entire 3 years worth of PayPal data into a single graph instance. Obviously, we have a much more powerful machine than the commodity servers we have. And we could load it in a single instance in GraphDB, and Neo4j is meant as a scale-up architecture. Because we store in GraphDB, we could index it, we could actually query different subgraphs, and we can apply a representation learning for different parts of the graph. So this, we found it extremely efficient to do any type of graph computing on top of the GraphDB rather than applying directly from the source. So the specific algorithm, we used Stanford's Node2Vec algorithm. We modified it to essentially the integration layer between the Neo4j and the Node2Vec layer. So Node2Vec is also built as a scale-up architecture where it is, as long as you have the entire graph data in a single machine, Node2Vec, you can operate the Node2Vec representation learning algorithm. The learned features are actually used as additional features in our space. So we are not at a point where we can completely use only the graph features to train our model. So we still use these features on top of the existing feature space and use H2O's driverless AI to train our model. Experiments actually, so these set of experiments, we use subset of 1 year transactions, though we have seen we could accommodate 3 years worth of transaction data. So these results for 1 year's worth of data set with 1.5 layers. This is the size of the graph data itself, and the total feature space is around 400 to 600, of which about 128 are from Node2Vec representation learning. So these are the tools. Node2Vec is open source. Again, driverless AI is commercial, and Spark cluster mainly used for data pre-processing and preparation of the data itself and ingesting data because our data is there in HDFS. So we use the Spark data processing pipeline to feed it into a Neo4j database. Most of the model training was done in a GPU-based computing. So this is actually some of the runtime results. So this is just to showcase how long it takes from laptop to GPU. Obviously, we don't build our models in laptops, so what it takes about 2 hours to build up on the same data set it takes about 20 minutes in a GPU compute, obviously, which I'm sure everybody is aware that GPU is the best suited hardware architecture for building deep network models and large-scale machine learning models. So this is actually final AUC on the OOT data set, out-of-time data set. You can see that we improved AUC by 3% by using additional feature space. So obviously it's 3%. For us, actually, it's some of our fraud models are so mature that it's extremely hard to get even a 0.1% percentage lift because of the years worth of research went into it. So that's why we don't eliminate any of them. So we just to see whether what else we can add to improve our existing models. We saw 3% improvement with this particular models, but obviously we don't use AUC as a measure, but I can share what the internal performance measure, but we did see significant benefit with on our internal benchmark as well. So 10% of the top 100 features are from Node2Vec, so we do see value in using Node2Vec representation learning features in our collusion fraud models. So to conclude, actually, we are seeing a significant performance lift. So driverless AI is also not only help to build a robust machine learning model, also engineer additional features on top of an existing feature space. So I forgot to mention that these were the representation learning was done on unweighted undirected graphs. So we are exploring adding different edge weights and modeling directed graphs and exploring these techniques. And the other key thing is that right now, the way some of these techniques are not robust to handle temporal changes in graph. Obviously, time is a critical dimension. You want to incorporate as part of the edge attribute. That's still an ongoing research in the graph modeling community, so we are still exploring. But the other alternate way is to retrain our model periodically, or relearn the vector representation, and if the representation changes, then you incorporate that to retrain your final model. And graph convolution is also another area we are exploring, where applying convolution-based architecture to learn additional feature representation from these. So so acknowledgements to H2O and Neo4j, we worked earlier last year, and we continue to work with them. H2O, we have active partnership with them, and we use Dell and NVIDIA's GPU accelerators to power some of this research. So I think I have time for, that's all I have. I couldn't hear the first question.
Yeah, I was going to say, what strategies have you thought about for weighting your edges based on association type or edge label? And then also, have you had to take into account random supernodes in your random walk, particularly with DFS and the fact that you have to have more walks to overcome them?
Yeah, so one other thing is this one was done in an unsupervised way, so we do have analysts. So we are working actually closely with, for example, some of the things we want to know. We want to label higher level features labeling for some of the node elements. For example, let's say that based on the activity the users are performing on the nodes, we want to say, is it a household type node, or is it a public Wi-Fi? Because the regular lookup for IP address, you don't give, that information is not robust, right? And also, is it a household entity, right? Or is it a household node? Being able to extract some of those higher level classification, so we can enable more good traffic in addition to preventing fraud. So we are working actively with the analysts as a semi-supervised way. So we have an active learning infrastructure. So because analysts cannot look at all of them, so we use a combination of representation learning in coordination with the analysts to how can we scale this to a much bigger data set, primarily around a semi-supervised learning case. So that's your first part. What was the second question, actually? Yeah, so the
second
supernodes.
question was, are you going to have to take into account supernodes for your random walk, in particular with the DFS use case?
Yeah, so that's, I think what my reason this thing is more than random walk, I think we are seeing some challenges beyond certain node size, so we have to actually even not explore nodes which are more than X degree. So where we are seeing much significant promises in the graph convolution area. So because we are seeing some limitations with the random walk, we are seeing better predictive results with the graph convolution. So that's the other area we are exploring instead of moving more towards the random walk based approach. So. Yeah, sure. Oh, so the question was how was the top 10% obtained? So the ranking is from the variable importance ranking from GPT. So if a variable occurs in most of the trees and top of the tree, those ranked higher than other variables as part of it. So the models were built using gradient boosted tree, and the top 10% was based on the variable importance ranking of the boosted trees. So top 10% of the variables which are. So that means those 10% occurs more on the top of the tree rather than at the bottom.
I have one question. Are the graphs like easily seen by an analyst as anomalous, the transaction graphs? Like, can a human spot out, hey, this looks suspicious, or is it some deeper thing that you're kind of teasing out of these graphs?
Actually, could you, I didn't get that.
Yeah, so as far as interpretability, so
yes.
Can like a human analyst seeing these transaction graphs, are they able to say that looks suspicious, or is it in combination with the other features allowing it to find some kind of other manifold of fraud?
Yeah, absolutely. I think the interpretability is extremely critical for us actually. So that's why we are working very closely with the analyst actually. So we have an analyst view of what they think the node classification should be, right? So, and obviously analysts don't have a complete picture of what is going on. So this is actually in augmenting, obviously with the representation, this is actually an active area of research, right? The whole thing with the deep learning, we lost the interpretability aspect of it, and probabilistic graph modeling actually is coming to that mix to how can we make our deep network model interpretable. That area is still, that thing is still true for these approaches as well. So right now what we are working is that we have analysts have labeled some of the nodes based on their intuition of how the fraudsters operated, and they are actually well experienced analysts and they are intelligent analysts. So we are working closely with them, and so far the results from the representation learning seem to match with what our analysts' intuitions are. But our measure of proof is in the fraud case anyway, so we don't have to go too much of the interpretability aspect of it, because we can prevent the bad guys from getting into the system, and we don't have to tell them why we are stopping them, right? So, so in that case, so the measure of proof is it actually providing a predictive lift on our downstream machine learning models, then hopefully it is capturing some characteristics which is not captured by existing feature space.
So kind of a follow-up question to what he asked. Do your analysis use like any sort of graph UI tool, visualizer, apart from Neo4j's own visualizer to kind of label everything? Yeah. Or is it something else that you use?
Yeah, actually we have found Neo4j's visualizations. One of the other advantage of Neo4j is that, or GraphDB in general, is that not only we can use to train the features, the results of our trained model we can, the predicted output can be first of all, can be inserted back into our GraphDB as additional attributes, so that the decisions can be much easier based on the trained model outputs. Yeah, so right now we are using Neo4j's inbuilt visualization as we also have a homegrown solution, so we are trying to see whether we can integrate that into an existing framework.
But as you already said, like Neo4j just scales up, it doesn't really scale out, right? So did you ever hit like some limits where you couldn't store more nodes and edges in Neo4j and you had to look for other solutions like maybe Azure Cosmos DB or something like that?
Yeah, so I think to me actually what we are seeing is more and more is on the Neo4j. So to me, if you have a graph DB, you don't try to stick in all the data elements into graph DB. Only the ones which are graph networks elements, only store those elements in that, then you can easily fit most of our data. So for example, we were able to fit 3 years worth of data set with most of the critical attributes which we need for graph modeling. We were able to fit in a single machine's database. So obviously our single machine is much more powerful, much more, we have terabytes of memory and a lot more cores in our, and we also have accelerators powered to a single machine. So we were able to fit in a single machine with that thing, so we haven't gotten any challenges into having to have scale-out models.
I have a question right here. More to your right. So what you showed for the node to vec extraction of the features, the examples that you showed seem to be some of the more classical features of centrality, connectiveness, community. What is the added benefit of using node to vec in these random walks versus the more typical algorithms for feature extractions, like network statistics in general?
Yeah, I mean, one of the things is obviously the traditional way to have some kind of graph attributes which we have is that, for example, you can get a degree, page rank, and a fixed set of formulations or mathematical functions which you can compute it on an existing graph structure and use this as additional features. The power of this representation learning is that it can automatically learn features from, and it can model much more complex graph structure. For example, the role they are playing. So if a particular node has different roles depending upon what role they are playing, whether it's a hub versus as part of a community. So the representation learning can model more variations of graph structure, and that's why I think we are seeing. So in fact, some of those features we are using today is we are using existing graph attributes obtained using traditional techniques, and this is actually complementing it, not actually replacing some of those additional ones. So.
Okay, and I just have one other question. If you can just clarify that the encoding and the data schema of the graph kind of drives everything that you do subsequently. So how you decide to model your graph is really key. And this kind of related to the weighted properties of the edges and so on, how you determine that. So have you figured out a way to figure out what the right encoding is, or to iterate through various encodings in order to figure, and data schemas in order to figure out what is the optimal for your problem?
Yeah, sure. Certainly, I think that is definitely an ongoing work for us. I think the algorithms which I used, they do support both weighted and directed graphs as well. So we still have to study what kind of encoding is actually right representing. But we are seeing incremental performance even with undirected and unweighted graphs. So hopefully we will get better results with including those.
All right, a round of applause for the speaker, and please don't stop asking.